Hello, everybody. Let me just get plugged in. What? Not. Oops. Right, it is time. All streams are go. Let me get everything up. Do a sound check as well briefly. Let's do a quick sound check. Is everything up? Hey, Twitter seems a lot better these days. Sound check, sound check. Sound check. Right. Don't have to do this every time, but it works. I wonder if at some point I could get this microphone mounted from above so it's not in the way of my hand and keyboard and stuff. That'd be kind of cool. I'm just thinking how I'd do that. A bit fiddly, but yeah. Where are we at? Let's check everybody's live here. Hope everyone's having fun tonight. I think we're pretty much just ready to get going, to be honest. We're here, got everything set up. It's time to go, I guess. Right. We're here. We're rolling, might as well get started. So let's just jump straight into it. So yesterday we finished off binary trees, and then we basically just opened up red-black trees. This course has been a real slog to get through. We've had quite a few episodes, streaming episodes on this now, but it's fine. It's what it is. This is a weakness of mine. That's why we're doing it. That's why we're going over it. So we get through this. There's still some hefty courses left. There's 101 lessons on learning memory management in C. There's another project. I remember, though, depending on what the project is, they sometimes take a bit of time, sometimes not. Learning Go, and that'll be a fair bit. Build a Pokedex in Go, learn SQL. Yeah, some of these are longer, but then, to be honest, when we've done these ones, the bulk of, I say the bulk, heck of a lot of this stuff is kind of done. And then it's just sinking hours into sessions with these. And then we've got the deeper courses, and whether we get to them by the end of the year, I'm not too sure. It'd be kind of cool if I could do them, because just completeness and my own satisfaction, I guess, and stuff, and kind of give a complete review of sort of like Boot.dev. But yeah, anyways, and then maybe come back to that one at the end, because I think that was introduced like kind of halfway through. So yeah, right, we're on red-black tree. So a red-black tree is a kind of binary tree that solves the balancing problem. It contains a bit of extra logic to ensure that as nodes are inserted and deleted, the tree remains relatively balanced. So let's have a watch of this video, and then we'll get started.
So regular old binary trees have a problem. They have no built-in protection against unbalance. If you insert an ordered list into a binary tree, you'll end up with a single branch in your tree, which is no better than a linked list. Your efficient order log n lookups degrade right down to order n. But a balanced tree is a fast tree. And by balanced, I just mean it's about as wide as it can be. It doesn't have these super long branches that take forever to iterate down. So how do we keep our binary trees balanced? Well, the red-black algorithm, or the red-black tree data structure specifically, solves this. Here's the big idea. When items are inserted and removed from a red-black tree, we have one little extra step. Take insertion, for example. After inserting a new item into a red-black tree, we have a fix step. And in the fix step, we check the state of the tree, and if it's starting to become unbalanced, we perform a rotation, which is basically just where we take the longer branch of the tree and fold it back into the rest, which flattens the tree as a whole. Now, first of all, don't let the colors red and black confuse you. They're really just a Boolean value that we attach to each node, true or false. The only reason we use the words red and black is so that it's easier to draw out and visualize. The idea is that every node in a red-black tree has this extra bit of data, its color. And we use those colors to know if the tree is sufficiently balanced or not. There are just a few simple rules. First, each node is either red or black. Second, the root is black. Third, all nil leaf nodes are black. Fourth, if a node is red, then both its children must be black. And fifth, all paths from a node to any of its descendant nil nodes, the bottom of the tree, must go through the same number of black nodes. Now, that last rule, that all paths from a node must go through the same number of black nodes to reach the bottom of the tree, that's the ticket. When a branch starts to get too long, we rebalance the tree by performing a rotation to make sure it still follows the rules. So let's focus on the rotation. That's really the most interesting part of a red-black tree. Now, rotations can work both right and left, but let's look at a left rotation. A right rotation is just the mirror of it anyways. So first, we start with this tree. 4 is the pivot, and 2 is the pivot's parent, and these are really the nodes that we're rotating around. First, we update the pivot's left child reference to now point to what was its parent, 2. Next, that left child that we just orphaned, 3, we make it the right child of the old parent. And that's it, we're done. All paths from a node must go through the same number of black nodes to reach the bottom of the tree. That's the ticket. When a branch starts to get too long, we rebalance the tree by performing a rotation to make sure it still follows the rules. So let's focus on the rotation. That's really the most interesting part of a red-black tree. Now, rotations can work both right and left, but let's look at a left rotation. A right rotation is just the mirror of it anyways. So first, we start with this tree. 4 is the pivot, and 2 is the pivot's parent, and these are really the nodes that we're rotating around. First, we update the pivot's left child reference to now point to what was its parent, 2. Next, that left child we just orphaned, 3, we make it the right child of the old parent. And that's it, we're done. Let me show that to you one more time. Now, it's important to understand this actually happens inside of a tree. So here's a visualization of the exact same thing happening inside a larger tree. And here it is again one more time.
Okay, makes sense. So how it works, each node in a red and black tree stores an extra bit called the color, either red or black. The color ensures that the tree remains approximately balanced during insertions and deletions. When the tree is modified, the new tree is rearranged and repainted to restore the coloring properties that constrain how unbalanced the tree can become in the worst case. So read that again. So how it works: each node in the red and a red and black tree stores an extra bit called the color, either red or black. The color ensures that the tree remains approximately balanced during insertions and deletions. When the tree is modified, the new tree is rearranged and repainted to restore the coloring properties that constrain how unbalanced the tree can become in the worst case. Okay, so the red and black, the red and black nomenclature is arbitrary. You could call them red versus blue trees, shouts to Rooster Teeth, or not even call it color at all. The important part is just that we now have two types of nodes, and that will affect the algorithm for balancing it. Okay, so list of very simple rules. So yeah, what about that? So each node is either red or black. The root is black. All nil leaf nodes are black. If a node is red, then both its children are black. All paths from a single node go through the same number of black nodes to reach any of its descendant nil black nodes. So it goes through one. So all paths from a single node go through the same number of black nodes to reach any of its descendant nil black nodes. So if I started here, not sure what it means by that. So that one, all paths from a single node go through the same number of black nodes to reach any of its descendant nil black nodes. So this red one goes through only one black node. Through here it goes through only one black node. Through here it goes only one black node, I guess. Okay. So this one goes through one black node. All right, okay. Oh, yeah. Okay, right, I understand how that works. Right, makes sense. So, this is why we stopped last night, because I saw this list and I was like, heck no, we're not doing that today. It's way too much. But we'll be doing it tonight. So, there we go. So here we are. So the assignment, as it turns out, we've been inserting user records into our tree with incrementing numerical IDs, pre-sorted data. The app's user lookups are starting to get really slow. Let's start implementing a red-black tree to speed things up. In a normal binary search tree, the child nodes don't need to know about or carry a reference to their parent. The same is not true for red-black trees. The RB node class is already implemented for you, as well as the init constructor method of the RB tree. There's also a data member, self.nil, created for you in the constructor. Okay. Self.nil contains the value we'll use to designate all the nil empty leaf nodes, which are used for rebalancing purposes but contain no actual value. Okay. Complete the insert method. It should take a value as input and add the value as a new node in the tree if the value doesn't already exist. So create the new node. Okay, so new node equals, that's going to be RB node, and give it the value it's passed in. The new node shouldn't have a parent yet. Okay, the new node's left and right child should be nil. Yeah. Well, not nil, I guess. The new node is red. New node.red equals true. New node.left Okay. So guess by default when that's created, parent is none, left and right are none. Well, it says nil, but you can't set it to a value of nil, right? It's just none. Okay. Find the parent of new node if there will be one. Initialize a parent variable to none. So we'll say parent equals none. Initialize a current variable to the root node of the tree. So current equals root node self.root. While current isn't a nil node, so while current is not equal to none. Set parent to current, so parent equals current. If the new nodes if the new node's value is less than the current node's, set current to its. So if new node is current, I guess is there a value? Yeah, okay. So if new node dot value so if the new node's value is less than the current node's, set current to its own left child. So current equals current dot left. If new nodes, so new node, node dot value is greater than current dot value, then set current to its own right child. Current dot right. If the values are equal, just return because this value is duplicate. So if new node dot value is equal to current dot value, then return. I think that's right. So then parent should now be a reference to the node that will become the parent of the new node. Parent should now be a reference to the node that will become the parent of the new node, okay? Insert the, we'll see if this is right at the end. Insert the new node by setting the parent's child. Insert the new node by setting the parent's child. So parents dot, so the new node's parent. Oh, hold on. New node dot parent equals parent. If the parent is none, we are dealing with a root, new root. So set the tree's root data. If the parent is none, so we have to do that check before we do that. So if parent is equal to none, we are dealing with a new root. So set the tree's root data member to the new node. So I guess it'd be self.root equals so the tree's root data to the member to the new node. Okay, otherwise compare values We just do that regardless. Else, otherwise compare the values of parent and new node. Otherwise compare the values of the parent and new node and set parents left or right child based on the results. So elif compare the values of the parent and new node. So parent dot value I have to do this again basically. Let's compare the values of the parent and new node. And set the parents left or right child based on the results. So it'd be parent dot left is equal to new node. I think that's it. Uh-oh. Otherwise compare the values of the parent and new node. Insert new node by setting the parent's child. Okay, I'm not sure which point I've introduced a infinite loop. Give it another try. Oh, I've got an infinite loop. I think that's right. We've kind of done all the steps, but which part is not right? So while current is not equal to none. Suppose it's that, isn't it? So at that. So we're getting through, we're getting an error down at the bottom stuff. So set the new node's parent to the parent we just found. Yep. Pretty sure of that part. So if the parent is none, we're dealing with a new root. So set the tree's root data member to the new node. So parent is none, self.root equals new node. Yep. Then I'm pretty confident that, so it's this part. Otherwise, compare the values of the parent and new node and set the parent's left or right child based on the results. So to be honest, I think nesting it like that would be the nicest way of doing it. What's wrong with it? 31. As we're done for now, we really just made another more complicated regular binary tree, seeing as it's not fully fledged red-black tree yet. But these upgrades will allow us to implement the rest of the logic in the next few lessons. So far, we've added a parent pointer from child to parent, so child know who their parents are. We've added mechanisms for coloring the nodes, but have defaulted them all to red for now. Okay, so what's the problem with this here? So line 31. So it's saying current object has no value. Okay. So if the new node's value is less than the current node's, set the current node to its own left child. If the values are equal, just return because it's a duplicate value. Okay. Something not quite right here, but I can't quite figure it out. So current. Initialize a parent variable to none. Initialize a current variable to the root node of the tree. So, yep, self.root. And then while current isn't a nil node, Set the new node's parents. So print parents. Let's pull this up a bit so we can see a bit more. Parent none. Oh. Right, important job of the day done. We're back. Okie dokie. So, there's somewhere in the logic where current is being set to the wrong thing, or there's not a check going on where it should. Uh, hmm. Okay. So it's saying object has no attribute of value. Current equals current left. It says if the new node's value is less than the current node's, set current to its own left child. Set current to its own right child. Whereas equal return because the value is a duplicate. So it's new node parents. New node parents. None. Whoops. Still none. So we print and we say parents and currents. Parents, currents. Put the value in so we can see what the value is. Value, value, and then current dot left, and then current dot right. So that's on the first loop around. Nothing touches current, right? And then it says current non-type object has no attribute value. Do I call on Boots, the Almighty? I don't think there's anything wrong with this. So the parent is Mitch number 7. That is the current value is Mitch number 7 as well. There is none and none, so like, is that so it doesn't mean any of those, so it will I'll just print here. So print um, less than greater than. So it falls into the greater than. That can't be right. My current isn't a nil node. While current isn't a nil node. I think it's that. It's a bit of a funny wording in there. Okay, so I got out of the infinite looping stuff. I guess return. Is that a no? Don't think it really matters, does it? Set current to its own left child. If the new node's value is less than the current node's, set current to its own left child. See, I feel like that's right though. This is right. It's just that when it's here, it hasn't got anything. Like it's just none. So it's set to none. I feel like it's just a bad wording or something for this part. Set current to its own left child. The thing is, current.left is empty. Is none. Does it have anything? Set current to its own right child. I'm gonna have to ask Boots, otherwise we'll be here all night. Oh, we've got how to use your pencil, paper, some kind of drawing to visualize the trees. You go through some in this chapter. Yeah, I'm gonna ask Boots. What am I missing? Oh, you got baked salmon. No, I'm just gonna sacrifice experience points. I can see your code and the error, the issue in your while loop, and how you're handling the nil nodes. The problem is that when you set current to current is current left or current is current right, you're getting none because you initialize the new nodes children as none. But then you're trying to access current value on a new. Yeah, no, so that's the part I get. But what am I supposed to be doing then? Looking at your code, I notice a few things need fixing. So your new nodes children should be self.nil, not none. Your new nodes children should be self.nil, not none. The red black tree uses self.nil as a sentinel value for empty nodes. Your new node children should be. How should you initialize the new nodes left and right children? You're missing the duplicate check. What should happen if the value already exists in the tree? Go back to this. So the new nodes left and right. So new node dot left equals self dot nil. New node dot right equals self dot nil. Okay, we covered that. So set parent to current. So while current isn't a nil node, so self dot nil. How should you initialize the new nodes left and right children? Yep. What should your while loop condition be to work properly with the self not nil sentiment? Okay, got it. So there's some misunderstanding about what nil was in the setting of things, but yeah, a little bit confusing, but never mind. Rules. So In addition to all the rules of binary search tree, a red and black tree must follow some additional additional ones. Yep, so we know that. Red and black trees are perfectly balanced. Hold on. So each node is either red or black. The root is black. This rule is sometimes omitted. Since the root can always be changed from red to black, but not necessarily vice versa. This rule has a little effect on analysis. All nil leaf nodes are black. If a node is red, then both its children are black. Blah, blah, blah. Perfectly balanced. The rebalancing of a red-black tree does not result in a perfectly balanced tree. However, its insertion and deletion operations, along with the tree rearranger and coloring, are always performed at O log n times. So, no, not perfectly balanced. Red-black trees always have worst case O log n, insertion, delete, ups, and lookup arrangements. I guess true. Yeah. Okay, with lesson 6, we've got rotation, fix, insert, and quizzes. Okay. So rotations are what actually keep a red-black tree balanced. Every time one branch of the tree starts getting too long, we will rotate those branches to keep the tree shallow. A shallow tree is a healthy, fast tree. A properly ordered tree pre-rotation remains a properly ordered tree post-rotation. So a properly ordered tree pre-rotation remains a properly ordered tree post-rotation. Rotations are O1 operations. When rotating left, the pivot node's initial parent becomes its left child. So the pivot node's initial parent becomes its left child. The pivot node's old left child becomes its initial parent's new right child. Here's the process of a left rotation. So start left rotation on a pivot. Old left child gets replaced by parent. Yep, so old parent is the new left child. Old left child becomes left child, the new left child. Old left child becomes new left child's right child. So pivot, new left child this becomes the right child of the left parent. Okay, complicated way of saying it, but I get the meaning. So assignment, now that we can add users to our new red-black tree, we need to add the rotation functionality that will keep it balanced and running fast. Complete the rotate left method. Rotate left method, it takes a single node, pivot parent as input and rotates the tree with its pivot node. Pivot parent. Pivot node, which in this case is its right child. So if pivot parent is nil or pivot parent's right child is nil, return. Nothing to do here. So if pivot parent is equal to nil, or pivot parent's right child is equal to nil, then return. Nothing to do. Let pivot be pivot. So pivots equals pivot parent's right child. Set pivot parent's right child. So pivots parent dot right. Set pivot parent's right child to be pivot's left child. So pivot dot left. Set pivot parent's right child to be pivot's left child. If pivot's left child isn't a nil leaf node, so if pivot dot left is not equal to nil, if the pivot's left child isn't a nil leaf node, set pivot's left child's parent to pivot parent. Set pivot's left child's parent. Oh my goodness. Pivot left dot parent equals pivot parent. So set pivot's parent to pivot parent's parent. Oh my goodness. Pivot dot parent equals pivot parent's parent. If pivot parent is the root, so if pivot parent is equal to self dot root, set the root to pivot self dot root equals pivot. Otherwise, if pivot parent is its child, if its pivot's parent is equal to its parent's pivot. Oh my goodness, pivot parents dot parent dot left. Set pivot parent's parent left child. Oh my goodness, pivot parent otherwise if pivot parent is its parent's left child, set pivot parent's parent's left child to pivot. Otherwise, if pivot parent, oh my goodness, pivot parent is its parent's right child, so equals pivot parent dot right child. So pivot parent's right child to pivot. So pivot parent dot parent dot right equals pivot. Oh, set pivot's left child to be pivot parent. So pivot dot left is equal to pivot parent, and then set pivot's parent to be pivot. So pivot's parent dot parent is equal to pivot. Complete the rote type method. Oh no, with Oh my goodness. Got to invert it, so complete rotate right method with all the directionality inverted. Oh my goodness. Ugh. So if parent is self-nil, parent left. Left, oops, left, right. So then, right, right. I don't think switching these matters, but I'm just doing it because I'm doing it all the way down. So pivot right. Huzzah! Oh yes, got it. Whew! Didn't need boots for that one. Kind of lucky. So fix, insert, and then we got two quizzes. Boy, God. Binary trees, yuck. Hash maps, tries, graphs, breadth first search and depth first search, and then P versus MP. I'm not sure what that is. Maybe we get through these tonight. It's we're not doing too bad. We conquered this a lot faster than I thought it was going to be, which is good. Which is good. How's everybody doing out there? Everyone having fun? Hope you're learning something. Hope you're having a good time. Anyway, so we got fix, insert. So rotations are only useful if we can use them. When new nodes are inserted into the tree, they can break the red-black properties. We'll fix that by rotating the tree as... Hold on, let me read that again. I read it without even thinking about it. Fix, insert. So rotations are only useful if we can... Rotations are only useful if we can use them. When new nodes are inserted into the tree, they can break the red-black properties. We'll fix that by rotating the tree as new nodes are inserted, ensuring the tree remains balanced. When we're done here, we will have a fully functional, albeit insert-only, red-black tree. As you can see, if you look at the bottom of the test suite, we'll be inserting numbers into our tree in order. A normal binary tree would break down into a single unruly branch, or like this. But our red-black tree will remain balanced. So, it's like, oh my goodness. Lane, you're putting us through the paces, my guy, you know. How do I do screenshots again if I get... hold on. Control mod print. Okay, so back to this. I'm just staring down the barrel of this big ass thing I need to do. So, my goodness. This is basically, I keep forgetting that you can just do like, you don't have to do equals on these things, if you just do is. It's kind of nice. Okay, complete insert method to call our balancing method after inserting a new node. So, call our balancing method after inserting a new node. So fix insert. Okay, so I guess self dot fix underscore insert. New node. Okay, so then complete the fix insert method that maintains red black tree properties. So while the current node, wait, what are we in? Tree, okay. While the current node is not the root, and has a red parent. So while current node, so new node. So while the current node is not the root, new node is not self dot root, and new node has a red parent. New node dot parent. New dot parent dot red is equal to true. Then do something. So while node is not the root, and new node as a red parent, identify the parent, grandparent, and uncle nodes of the newly inserted node. So parent equals new node dot parent, grandparent, the newly inserted node. So grandparent equals new node dot parent dot parent. All right, parent dot parent, and then the uncle nodes of the newly inserted node. If the parent is a oh my goodness, right? So uncle, we'll call it uncle left and uncle right. Uncle left is a new node dot parent dot left, and then uncle right equals new node dot parent dot right. Okay. If the parent is a right child of the grandparent, so if parent is equal, I guess we could do is a right child of the grandparent, so grandparent dot right. Then uncle. Uncle nodes. How do you find the uncle node? Because you got the parent, but the uncle could be left or right, couldn't it? Hold on. So the parent is just the parent, the grandparent is the parent of the parent. The uncle, well, it can only have two. So we have to work out, we think. Whether it's left or right. Uncle is parent dot left or new node dot parent dot right. I'm not sure how you do that, but I don't know if that'll work, but we'll see. Basically, if can you do that? So Python conditionally set variable. So bit of a messy way to do it, but so if the parent node left is equal to the new node, and do that. I'm not sure how well that does, but anyway. We'll carry on. So think I've done that. I'm not too sure. So if the parent is a right child of the grandparent, if the uncle is red, so if uncle dot what is it? Dot red is true. If the uncle is black, so then recolor uncle and parent to black. So uncle dot red is equal to false. Parent dot red is equal to false. Recolor grandparent to be red. So I guess grandparent dot red red equals true. Move up the tree by making the current node the grandparent. So new node equals grandparent. Else. I think that's right. Grandparent. So then if the uncle is black, if the current node is left, if new node is left child of the parent, so parent dot left, then move up the tree by making current node the parent. So new node equals parent. Rotate right around the current node. Self dot rotate right around the current node. Rotate right. New node. Set the parent to be the current parent. Set the parent, so parent equals to be current node's parent, so node dot parent. And then recall the parent to be black, so parent dot equals false. Recall the parent to be black, yeah. So recall grandparent to be red, so grandparent dot red equals true. Rotate left around the grandparent, so self dot rotate underscore left the grandparent. I think that's fine. If the node is the left child of the parent. So there, if grandparent, so outside this if function, then we have a if the parent is a left child of the grandparent. So parent is grandparent dot left. So then we got kind of like the same stuff going on here. So I'm just going to copy this, paste it. So if the uncle is red, recolor uncle and parent to be black. Recolor grandparent to be red. Move up the tree by making current node the grandparent. If the uncle is black, if the current node is the right child of the parent, So there, switcheroo. Back if the current node, and then move up the tree by making the current node the parent. Rotate left around the current node. Set parent to be the current node's parent. Yep. Recalling parent to be black, grandparent to be red, and then rotate right around the grandparent. And then recolor root to be black. So then outside all this, so then recolor root to be black. So self dot root dot red equals false. Okay. So close. Say close, not really. I feel like maybe this is the point where it falls down, finding the uncle. I might be. Because how do you know which one's the uncle? You have to know if this is a left or a right, yeah? So you have to know if the new node, if it's a parent of the left. So if the parent left is new node, then uncle is Python ternary operator. Let's have a look at this. So say by default, it's the left child, but if so it's going to be left child if left child is, by default, it's going to be left child if so close is closer. Not really sure, to be honest. So left child if the parent left is not, so this is part, if it's true, Let me step through it. So I think that's done properly now. So if the new node dot parent dot left, if the right child of the parent is a new node, then we want uncle to be the left. Uncle is clearly the left one because it can't be the thingy one. And if oh, hold on. Hold on, the uncle of this new node is a level above. So it's grandparent. Right, that gets into right order. Right, okay, I've got my head around. So there's just one colouring going wrong. So let me trace it through. So if the parent is a right child of the grandparent, then if the uncle is red, recolour uncle and parent to be black. So uncle and parent are false, red are false. Grandparent, red is true. Move up the tree by making the current node the grandparent, yeah. And then else, if the uncle is black, I guess I might as well check it, like, so L, if uncle dot red is false. Don't suppose it really change it, but might as well try it. Then if it's black, if the new node is the left child of the parent, move up the tree by making the current node the parent, rotate around the current node, parent, set the parent to be the current node's parent. Current node's parent, yeah. Parent is black, grandparent is red. Rotate left around the grandparent, and then if the parent is a left child of the grandparent, then if the uncle is red, change so it's thinking uncle red is false. So recolor uncle and parent to black. Yeah, recolor grandparent to be red. Move up the tree by making the current node the grandparent. And then if the uncle is black, if the current node is the right child of the parent, move up the tree by making current node the grandparent, and then rotate left around the current node, set parent to be the current node's parent, and then parent is black, grandparent is red, rotate right. Okay, so it's a bit moink. Not quite. Right, Boots. Come on, Boots. Help me out here. Can you do it for free? I don't even know how I got this summon to begin with, to be honest. Oh my goodness, Boots. Crikey. Okay, whoa. I can certainly help you with your code, young apprentice. Boot.dev offers a variety of ways to learn and practice. If you're curious about different access levels, you can check out the details on our pricing page. Allow me to access our pricing page. I've got it. Yes, I can definitely help you with debugging this red black tree implementation. All the content on Boot.dev is free to access, including lesson, explanations, start code. Okay. Progress tracking, gamification, IXP, blah, 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 blah. Chats with Boot Me, certification is completion. Access to higher tier Discord levels, use of Boot.dev CLI. Yeah. So the first feature, okay. Now let's get back to your code. So it looks like you're having issues with the fix insert function, specifically the rotation logic and color changes as expected, and actual outputs differ in the color of some nodes. Let's break down fix insert function and review the cases. So you have two main if blocks for parent is grandparent right and parent is grandparent left. Within each you have subblocks for uncle is red, uncle is red false. Consider the case where parent is grandparent right and uncle is red true, your code. Yeah, this looks correct. If the uncle is red, you recall the parent, uncle and grandparent, and then continue the loop from the grandparent. Now consider the case where parent is grandparent right and uncle red is false. So your code, okay? Yep. So in this scenario, the new node is the left child of the parent, which is the right child of the grandparent. It's a triangle case, and a right rotation is needed on the parent before the final rotation on the grandparent. This seems correct. The issue might be in how you determine the uncle node. Let's re-examine this line. Yeah, I thought so. I had it. So this line is incorrect for determining the uncle. The uncle is the sibling of the parent node. If parent is the right child of grandparent, if parent is the right child of grandparent, then uncle should be grandparent left. So if parent is the right, oh, was that it? It's literally, I'm so dumb. I got it. Yeah, cheers, Boots. Okay. I did it. I just did it kind of like a step before. Oh, quiz, finally. And hopefully we can squeeze out hash maps tonight. Gosh, this course is modules long. Okay, so red black tree rules. So each node is either red or black. The root is black. This rule is sometimes omitted, since the root can always be changed from red to black, but not necessarily vice versa. This rule has little effect on analysis. All nil leaf nodes are black. If a node is red, then both its children are black. All paths from okay. So is the tree displayed a valid red black tree? Nope, it breaks rule. No, wait, hold on. Each node is either red or black. If a node is red, then both its children are black. Yes, I guess it's valid. No. All nil leaf nodes are black. Oh. Breaks rule number 4. Because That can't be red, that must be black. To be a valid red-black tree, a black node must have red children. No. False, it doesn't matter. Woo! Ugh. Gosh. Jeez. Chapter 12, hash maps. We've got 10 lessons in this. I think we can squeeze out 10 in this, but we shall see. Oh. Okay, right. Let's get back to it, see if we can get through hash maps in one night. 10 lessons, is it? Yeah, 10. Okay, let's see. So, hash maps. A hash map or hash table is a data structure that maps keys to values. So, the lookup, insertion, deletion operations of hash map have an average computational cost of 0.1. Assuming you know the key, nothing beats a hash map. A Python dictionary is an example of a hash map. See, you already know what a hash map is. Under the hood, while hash maps... Oh, goodness. While hash maps are simple to use, you're already proficient with them. If you know how to use a Python dictionary, the implementation is a bit trickier. So hash maps are built on top of arrays, or in the case of ours, a Python list. Oh, top arrays, yep. They use a hash function to convert a hashable key. A hash function. All right, okay. Yep. They use a hash function to convert a hashable key into an index in the array. From a high level, all that matters to us is that the hash function. They use a hash function to convert a hashable key into an index in the array. From a high level, all that matters to us is that the hash function takes a key and returns an integer. Always returns the same integer for the same key. Always returns a valid index in the array, not negative, not greater than the size of the array. Case of this example, so Ross, to store the value of Ross at key Bob, hash function Bob goes to 3. Insert value Ross at index 3. To get value at key Bob, hash function Bob goes to 3, return the value at index 3. Ideally, the hash function hashes each key to a unique index, but most hash table designs employ an imperfect hash function, which might cause hash collisions, where the hash function generates the same index for more than one key. An example of a collision in the above example would be Bob and Leonardo both hashing to index 3. Ideally, Leonardo would hash to some other index like 2. Such collisions are typically accommodated for and are not a problem in practice. Hash maps use arrays under the hood. Okay, same thing. What is the big O complexity to iterate over all the keys and values of a hash map? Hint, this is a trick question. This is a trick question. O-N? Oh, explain why it's a trick question. Of course, the question was, what is the big O complexity to iterate over all the keys and values in a hash? Correct answer is O-N. Let's break down why. When you iterate over all keys and values in a hash map, you have to visit each entry once. If there are n entries, you'll perform n operations, one for each key value. Regardless of how fancy the data structure is under the hood, hash tables are very efficient for individual lookups, insertions and deletions using usually O1. Looping through every item still requires looking at them one by one. That's why, yeah, makes sense. I should have just known that. Another question. So hash maps can, in most cases, map keys to values. Hashable keys to any values, yeah? Okay, let's explain that again. Like, I'm pretty sure, because it says has to have a hashable key, any value. So, an excellent question, but it's break down hashable, any, its correct answer. So, understanding hashable keys. So, the key insight is in the word hashable. Not all data types can be used as keys in a hash map. A key must be hashable, which means it can be converted into a hash, an integer, by a hash function. Its hash value never changes during its lifetime. It's immutable. Objects that compare as equal must have the same hash value. In Python, examples of hashable includes strings, numbers, tuples if they contain only hashable elements, and frozen sets. Examples of non-hashable types are lists, they're mutable, dictionaries also mutable, and sets mutable. Understanding any values. For the values in a hash map, there are no such restrictions. You can store literally anything as a value. So strings, numbers, lists, other dictionaries, custom objects, functions, anything. Why the other options are wrong. So string, too restrictive. Keys can be more than just strings, and values can be more than just strings. String any, still too restrictive for keys. Numbers, tuples, and other hashable types can also be keys. Int any, again, too restrictive. Okay. Okay. So let's build a toy hash map in Python. In the real world, you would almost always use the built-in Python dictionary if you need a hash map. However, just using a dictionary doesn't teach us about what's going on under the hood. Assignment. As it turns out, the binary search tree was overkill for the profile lookups on the locked-in website. We don't need any fancy ordered traversals or range queries after all. And because locked in is such a business failure, our CEO's words, not mine, we can store every user in memory. No need to save them to the hard drive. Let's build a hash map. We'll use the strings, usernames, as keys and map them to user objects. Complete the hash map's key to index method. It should take a key string as input. Yeah. Calculate the sum of the Unicode values of all the characters in the string using Python's ORD function. Sum of Unicodes equals ORD key. How does that work? Given a string representing a Unicode character, return an integer representing the Unicode point of that character. For example, ORD A returns, okay, the inverse of character. Given a string representing one Unicode character. Can I do it like that? Can I pass a whole string? We'll see. Mod percentage the sum by the size of the hash map to get an index, which would be an int. So index equals mod the sum by the size of the hash map. To get an index, which would be an int. Return index. So mod the sum. So sum of, of Unicodes mod size of the hash map. So what? The size of the hash map. Or k in key sum Unicodes plus equals odd k, like that. Mod the sum the sum by the size of the hash map to get an index. Size of the hash map. Like that. Python get size of hash map. Where is oh, I suppose it's here, isn't it? Right, okay. Didn't realize that. Boop, got it. Okay. Insert. So character in key, some okay. So now that we have some building blocks for our hash map, we need a way to start inserting values. So assignment, complete the insert method. Accepts a string key and an associated value, in this case, locked in user record. So convert the incoming key to the appropriate storage index using your existing hash function. So storage index equals self dot key to index, and it'll be a key. Create a key value pair as a tuple. Oh, forgotten. Tuples. Tuple. So key value equals a key value like that. Store the tuple at the calculated index in the underlying array. Indexes with an entry will contain a tuple, and empty index will contain a non-value. Okay. So then store the tuple at the calculated index using the. So we're going to do self.hash map. And then it's going to be storage index equals key value. Like that. Boom. Got it first time. So get. Now that we can insert our users and their records into our hash map, we need a way to retrieve that information when requested. So the assignment, complete the get method. It takes a key, string, and returns the value stored at that location, not the whole key value tuple. Use the key to index method to find the correct index to look up the self hash map data store. And if a value doesn't exist at index, raise the following exception to indicate no result was found. Due to our simple implementation, some of the keys that inserted in the hash map will have colliding values, which may lead to strange results. That's okay. Okay, so correct index equals self dot key underscore to index key and then value equals self dot hash map correct index, and then will be if value is none, then that, else return value. Crap. You need to remember how to use tuples a little bit better. Oh, so I can do like key value like that. That's nice. Like destructuring. So it still failed. Exception, sorry, key not found, cannot unpack, non-interpretable, type of none. So I guess we need to do the check. Use the key index for providing the right index look up self hash map if a value doesn't exist at that index, I guess. So print here key value. Does it blow up or does it just say Nope. So here, tuple is none. Otherwise, tuple 1. That work? Nope. There we go. Got it. Hash map review. Boom, are we at the end? Oh yeah. Well, we got 2 quizzes and then some thingy, and then we got 2 done in one night. Tries, graphs. Oh my goodness, like we maybe another 2 sessions to get these done. Blimey, what a slog. Hash map review. So hash maps are awesome. They're simple to use and have an average computational cost of 0.1 for lookup, insertion, and deletion operations. So just use a hash map. We'll start by building a balanced red-black tree, and then once we have that, we can build a sophisticated, just use a hash map. So in Python, that means dictionaries. In Python, that means dictionaries. In Go, it means maps. In JavaScript, it means object literals. The point is, if you need an in-memory key value store, hash maps are awesome, and every language tends to have a built-in implementation. Properties of good hash map. Fast lookup. Hash maps have an average time complexity of 0.1 for lookups, insertions, and deletions. Unordered hash maps typically do not guarantee any particular order of keys. No ranging. While hash maps are great for lookups, they don't provide the ability to look into a range of keys, the largest 10 keys. That's one reason production databases like Postgres use binary trees for indexing. Collision resistant. Hash maps are built on top of arrays and use a hash function to convert a key into an index. Production ready implementations like Python dictionaries handle hash collisions and make them a non-issue in practice. Hashable keys. Keys must be hashable. This means they must be immutable and have a consistent hash value. For example, in Python, a tuple can be a key, but a list cannot. Efficient resizing. When a hash map's capacity is exceeded, it dynamically resizes, usually by doubling in size, and rehashes the elements. A good hash map manages this resizing efficiently, minimizing performance hits. A uniform distribution. A good hash function ensures keys are distributed evenly across hash map's underlying array, minimizing the number of collisions and optimizing lookup speed. So our toy hash map. It has a few big problems, but at least it's valuable for understanding the concept. Some of its big problems are it doesn't resize when it gets too full and doesn't handle collisions. Its hash function is simplistic and doesn't distribute keys evenly. What happens to our toy hash map if AB and BA are both used as keys? BA are both used as keys. They would collide because they have the same Unicode sum, yet program would crash. The data would be stored in the key BA because it's badass. The data would be stored in the key AB because it comes first alphabetically. So they would collide because they have the same Unicode sum. Which is a major drawback of our hash map as opposed to a more robust implementation. Its basic insert operations are slower than 0.1. It isn't ordered and doesn't support range lookups. It allocates a large list in memory, even when we haven't filled in the indexes. Our toy hash map. Its basic insert operations are slower than 0.1. It isn't ordered and doesn't support range lookups. It allocates. I guess it's that one. It allocates a large list in memory. Let's have it explain this one because I'm curious. I think it's because like it was saying like some keys in the hash map have no values. So let's look at the choices. Not true. A simple hash map in the average case, the basic idea is a hash map to 5 hash inserts. It isn't ordered. While this is true, it's not a drawback. Unique time implementation, most hash maps don't have that. Allocates large lists. This is the big drawback. Our time implementation, like many naive hash maps, pre-allocates an array or list of fixed size, even if we only use a few slots. So in contrast, yeah, okay. Can't remember the code from that stuff, but yeah. Yes. See, yeah. So resizing. Oh boy. Resizing and linear probing. Oh my goodness. Putting us through the paces tonight, Lane. Let's see if Lane replied. Thanks, Lane. Thanks for liking that. Crazy. Anyway, so resizing. Oh my goodness. So resizing. So in the current implementation of HashMap, our HashMap has a lot of collisions. This is because we're using fixed size for our HashMap. Okay. Okay. To reduce the chances of collision, we can increase the number of slots in a hash map. This is called resizing. This will not eliminate all possible collisions, but will help reduce the chance of one happening. When resizing, we create a new hash map with. When resizing, we create a new hash map with a larger number of slots. Then we reinsert all the key value pairs from the old hash map into the new hash map. To complete the current load method. Okay, so assignment. So it returns the number of filled buckets in the hash map as a ratio of the total number of buckets. In a hash map, a bucket is simply a slot that stores one or more key value pairs. So if the length So if the length of the underlying list is 0, return 1. So if self.hash map is equal to 1, then is 0, then return 1. Otherwise, divide the number of filled buckets by the length of the underlying list. So underlying list length equals underlying list length is that. Otherwise, return the number of filled buckets by the length. So number of filled buckets divided by underlying list length. So then I guess here we're going to get the number number of filled buckets equals change the number of filled buckets in the hash map. The ratio of the total number of buckets. In a hash map, a bucket is simply a slot that stores one or more key value pairs. Otherwise, divide the number of filled buckets. So in a hash map, a bucket is simply a slot. In a hash map, a bucket is simply a slot that stores one or more key value pairs. So buckets in self.hash map. If bucket is not none, then number of filled buckets plus equals 1. Something like that. Whoops, forgot. Nah. Otherwise, divide the number of filled buckets by the length of the underlying list and return it. So print self.hash map. I'll keep that for now. I'm not sure about this. Complete the resize method. So if the length of the underlying hash map is 0, make the length 1 by just adding a non-entry. So do that again. So I get self.insert, and it's going to be a non-entry. I'm not sure about that part. Get the current load. If it's less than 5%, do nothing. Load underscore percentage equals self.current underscore load. So if load percentage is less than 5, then return then return, and then otherwise store the current hash map in a temporary variable temp. It's called hash map equals self.hash map. Create a new empty hash map that's so new hash map equals hash map. I have to put new in front of it. New, no, hash map. New hash map that's 10 times the size of the current one. So 10 times underlying list length. And all the key value pairs from the temporary variable into the new hash map. So then, I guess for entry in temp hash map, new hash map dot insert it's going to be a key value. It's going to be key value. I think I got that. I'm not sure about this part, so whoops. Oh no, I went back a lesson. Oh no, oh no, 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 no. No, don't go there. Accidentally jumped a chapter somehow. Oh, got something going on. This part I'm not too sure of. So it returns the number of filled buckets in the hash map as a ratio of the total number of buckets in the hash map. A bucket is simply a slot that stores one of the key values. Length of the underlying list is 0, return 1. Otherwise, divide the number of filled buckets by the length of the underlying list and return it. Yeah. I have to call on Boots. We're getting close to time, so what's wrong? So, hey, Boots. I will reduce my XP score. I can see your code and the output. You'll gain a maximum recursion depth. It means there's some sort of infinite recursive loop. Let's think through your code step by step. So in your resize function method, when underlying list is 0, you call self insert on. Yeah, what does self insert do? It immediately calls self resize. Again, that means you're stuck in the loop between insert and resize. So it's a correct clue. What could you do when this internal list is empty that doesn't call insert? Is there a way to just create a single empty slot directly? All right, okay. Right. So I guess dot hash map dot append. Guess we could just put none like that. Also, another question: if your resize method, if the load percentage is less than 5, check what does current load return, and what should you compare it against if you want 5%. Try think about units comparing. Okay, yeah. Yeah, I know it's probably not 5%. I wasn't really sure what it was, so I guess if we did print load percentage, load percentage. Oops. Where is it? Times by 100. Load percentage is 0. Load percentage. So there's something wrong with the current load this part. So I think this is right. Otherwise, so I guess print buckets. Let's just print return ratio. That's going to be number of filled buckets and underlying list length. So it needs to care what the bucket is, and then that there is kind of whatever. So return ratio 0 to 1, so 0 divided by 1, 0. Let's divide the number of filled buckets by the length. So it's just the other way around, wrong way around. No, it's the right way around. I'm kind of stuck still. So I see your code and the output. You no longer hit the infinite recursion, but your hash map is not resizing updating as expected. Size is always 1 after the first insert and load stays at 1. Let me nudge you towards the cause. So after resizing, everything's still good. Cool. After resizing, are you actually updating yourself to hash map to use the new larger hash map? When reinserting key value pairs, are you handling non-values correctly? Oh. So tuple, okay. So if a tuple is none, then I guess return. Otherwise, key value equals tuple. After you go through the line storage, how do you actually become the new hash map? When copying items from the old to the new hash map, how can you avoid problems? Okay, so after resizing, you're actually updating yourself that hash map to use the larger resize. Closer? You're definitely getting closer. I can see the latest changes in the output. The error you're hitting object hash map in the length is caused by this line in your resize method. So self new hash map. Right now, your hash map is an instance of your hash map class, but your code self hash map to always be a list, not a whole hash map object. What attribute of a new hash map holds the list of buckets like the self hash map? Dot hash map. Boom. It's about knowing where goes where. Linear probing. Oh, definitely last one tonight. I'll tell you that. let's finish this off for tonight. So linear probing. In the previous lessons, we've built a basic hash map that can add and retrieve key value pairs. However, our current implementation does not handle collisions well. In the context of locked in, we want to make sure that user information can never be lost or overwritten. Collisions happens when two different keys have the same index after applying the key to index function. To handle collisions, we use a technique called linear probing. Linear probing works by finding the next. Let's read what it says. Linear probing is scheme computer science resolving collisions and hash tables, and look up individual blah blah blah. Linear probing is a form of open addressing these schemes. Each shall have, okay. Linear probing works by finding the next available slot after the collision index and placing the new key value pair there. Complete insert and get methods. Oh my goodness. So, okay, insert. Compute the index for the key. Compute the index of the key in the hash map. Self key to. So index equals self dot key to index key, and then we're going to initialize a Boolean variable. Create original index variable and assign it to index. Original index equals index, and then initialize a Boolean variable. First iteration equals true. Begin a while loop that continues as long as the hash map slot at index is occupied. So begin a while loop that continues as long as the hash map slot at index is occupied. Not none. So while index is not none. If this is not the first iteration, if first iteration is false. If it's not the first iteration and the current index, and index equals original index, raise an exception hash map is full. So raise, it's just like raise exception, or is it hash map is full, this means we traverse the entire hash map without finding an empty slot. Increment index by 1, so index plus equals 1, and wrap it around to the start of the hash map if necessary using module operator with hash map's length. Set first iteration plus after first iteration, so I guess first iteration equals false. Increment index by 1 and wrap it around to the start of the hash map if necessary using module operation with hash map's length. Uh-oh. Okay. Insert key value pair at the found index. Key value pair at the found index self hash map like that. I'm not sure about this part, we'll come back to it. Okay, the get. So compute the index for the key in the hash map with self created. Same thing. So initialize. Yeah, I've already kind of done this. So initialize boolean first iteration to true. Begin a while loop that continues as long as the hash map's slot at index is occupied. Okay, hold on. It's going to be self.hash map. So while so the hash map slot at index is occupied, not none. Begin if the key in the current index matches the key being searched. So So if the key at the current index if the key at the current index matches the key being searched, return the value from the key value pair in the hash map at the current index. So I guess if the key at the current index, so if the key at the current index if the key at the current index matches the key being searched, okay, let's go at index return the value from the key value pair. So then return value index. Okay, that I think is right. So if this is not the first iteration and the index equals the original index, raise exception, sorry, key not found. So sorry, key not found. This means we traverse the entire hash map without finding a key. If the key does not match, increment index by 1, So if set first iteration to false after the first iteration. If the while loop completes without finding a match, raise exception. Sorry, key not found. I'm not sure about the modular part. I'm gonna need some backup. Yeah. Yeah. So I can see your code and found and the error output. It lists out range errors because your index is going beyond the bounds of your hash map array. So let me help you spot the issue in your assert method. Yeah, I know it's this part. This is the problem, yeah. When you do index plus 1, you're not wrapping the index to the beginning of the hash map where it reaches the end. So your hash map has size 2 and your index becomes 2, you'll get out index range because the indices start from 1 to 0. What operation should you use instead of index plus 1 to make sure the index wraps around to the beginning of the hash map when it reaches the end? Think about what mathematical operation would turn 2 back to index 0 in a hash map of size 2 or index 3 back into 0 3. You have the same issue in your get method too. I know Boots, but my math sucks. No worries, young apprentice. The math here is actually quite simple. You need the modulo operator. It's like a division, but instead of giving you the result, it gives you the remainder. So, for example, 5 modulo 2, 5 modulo 3 is 2 because 5 divided by 3 is 1, remainder 2. 7 divided by 3 is remainder 2, yeah. The cool thing about modulo is that it automatically wraps around. So in hash map size 3, indices become, okay. So instead of, that, so index is going to be index plus 1 divided by the length of the hash map. This will increment the index by 1, but if it goes past the end of the hash map, it wraps around to 0. Yeah. I can't conceptually sort of like understand how that works in my head. So say if it was like, it was at 2 plus 1 is 3. And then 3 modulo so 3 modulo 2, 3 modulo 2, because 3 divided by 2 in a hash map of size 3, indices come, so when it gets to 2, it'll be 3 modulo 3 0. All right, I see. Yeah. Okay, right, I get it. Boom, shakalaka. Whoa. Okay. Right, we are on to chapter 13 tries. So I guess tomorrow, what day is tomorrow? Wednesday. Tomorrow we're going to be doing chapters 13 and 14. So that'll be it. That's it for tonight. So that's all I got for you tonight. Hope you've had a good time. You've learnt something. It's been funny watching me fail again and again, but this is why we learn these things, because we want to skill up. We're going to get much better. So if you've been watching, thanks for coming down. If you're going back from the future, again, let me know where you get that